So now let's have a look what the fuss is all about. I'll spare you the history and everything. You can basically watch as a documentary on YouTube. The main motivation, I think, for deep learning right now is that it simply works. It also comes with a big promise, which is basically just collect enough data and label it, and you can build a magic black box that will predict you any correlation that you can probably read out of that data. So I'm saying it that way because really only the supervised setting works reasonably well right now in an industrial environment. And there are other directions trying to learn and to map data in a more intuitive way, but really what caused the revolution was the supervised setting. Deep learning is big data, and it also comes with big money right now, which means the entire environment is highly competitive and also to some degree quite poisonous. A lot of competition usually comes with some toxic environments. Deep learning can also be dangerous. Think about deep fakes, think about what I did in the beginning with Einstein. There are things called adversarial attacks, which essentially cause your computerized algorithms to probably predict something undesirable, like your next insurance application or treatment in a hospital for some undesired human beings, probably. So it can be quite dangerous because it's also a relatively new field with little regulation. Anyway, we will be considered with the technical aspects of deep learning, and really what you should take away from this course is how to build such systems. And the main systems we are concerned with are basic feature extractor systems. So we want to map a really high dimensional space to something lower dimensional with which we can work with. Think back to your examples from the machine learning courses, house price estimation, or any other related toy examples where your input parameter space is reasonably small, something from 10 to 100 parameters. And fitting a linear model to this is not too difficult. You can even do it in closed form. Now, for highly complex data like images, like natural language, like really complex and extremely high dimensional data, that's not so easy anymore. And you need something that extracts you features that are as representative as possible. That's also why the entire field is sometimes also called representation learning, because we try to map high dimensional spaces to lower dimensional spaces that still represent that data extremely well. Now, following this feature extractor, you can use traditional machine learning methods or any task-specific heads on these pipelines for classification, regression, synthesis of data, whatever comes with it. But really, at the beginning of the course, we are concerned with the feature extraction, which is mainly convolutional neural networks and how these work. Now, an interesting question is, why did neural networks actually fail so far, or until probably 10 years ago, in doing basic tasks, like, for example, image analysis? The image analysis challenge set off in the 60s with a summer project, and it's still not entirely solved. So the task is rather simple. Say you take a 32 by 32 by 3 input image, and I know this is rather small here. Then you can simply take this entire image, put it in a 3072 by 1 vector, and deploy a, say, standard neural network to it. So you have a number of weights. You multiply this input vector with the weight matrix, and then you follow it with an activation function, right? So that doesn't work. It works to some degree, probably on 32 by 32 by 3 images, but it clearly won't work for images coming out of your mobile phones. So the traditional model failed so far, and the main reason is basically the curse of dimensionality. You might have heard about it, but really what I want you to understand here is what effect this has on these kind of machine learning models like a neural network. So the curse of dimensionality is defined in various ways, and sometimes it's a bit difficult to understand it because it's quite unintuitive. Essentially, it says as the number of features or dimension grows, the amount of data we need to generalize accurately grows exponentially. The formal definition is to approximate a Lipschitz continuous function from an arbitrary dimensional space to another smaller dimensional space. With epsilon accuracy, one needs order of epsilon to the power of minus d samples. Okay, so if you think about that, it means that your input space becomes less and less representative the more features you extract. And in the worst case, feature means every input sample of your sensor, probably every pixel of your image, right? And so straightforward classifiers have a really hard time to generalize in these settings. Now, let's think about an example here. So if we, for example, try to do a cats and dogs discriminator, and I'm not talking images here, simple parameters like body weight or body size or furry or less furry, any of those, then, well, a feature in this context is just one of these parameters. So we could decide to just choose one of these features and try to build a discriminator on them. We probably might decide to do something like a k-nearest neighbor discriminator, where really we just try to fit a small cube or hypersphere around k nearest examples and then take the closest one to the current example we're exploring. So if we, for example, look at one single parameter, body weight, for example, then here on this one-dimensional scale, they seem to separate somehow, and say k equals 5 nearest neighbor classifier would do something like this for a sample here, and the closest, well, the way I drew it, the closest seems to be this cat, so it will just steal the label from this closest sample in this hypercube, well, actually line segment in this case. So what you will observe is that it doesn't work very well. It will have a lot of false predictions in here. So probably we would like to decide to take another feature and add this to regularize our discriminator for cats and dogs. And if we have two parameters like here, our feature space is two-dimensional, say body weight and body size. And our discriminator generates a box like this as a decision boundary. We can go 3, 4, 5, 6 parameters to classify here. Now, if we look what this means in terms of sample density, like in this example here, in this very, very simple example here, I have 10 samples. Okay, probably in the world there are billions of cats and dogs. But because of resource limitations, or who knows, I have only 10 samples of cats and dogs here. So 5 cats and 5 dogs, and build that. So our feature space here, say in the one-dimensional case, if this is here, it's drawn like 5 units. This feature space is reasonably densely populated with our 10 samples here, right? So 20% of the samples are 0.2% of that line are populated with samples. So if we calculate the sample density, it's basically 2 samples per interval here. Now in 2 dimensions, that looks already a bit different. And in 2 dimensions, we have basically 20% of the samples here is 0.45 squared. So 5 by 5, 25, so it's 5 by 5 square. So this here covers 25 unit squares. If we calculate the sample density on this sub square, we only get to 0.4 samples per interval. So our space gets sparser, right? We still have only 10 samples, but we decided to make our feature space bigger. In 3 dimensions, it's if we go to 5 samples along this line and along this line and along this line. In 3 dimensions, it's even worse. So we have 10 over 125. So we have 125 unit voxels in this cube. So we have only 0.08 samples per interval.
Okay, this is me about 1.5 years after I've recorded the initial video for this topic. And let me try this again. I'm here on a Sunday in January 2022, and we'll try this until it works out. So this core problem here, the curse of dimensionality, is, I understand, it's really difficult to comprehend. Now probably the easiest way to imagine what's happening here is if you fix a few parameters and then imagine what happens to your samples. So for example, what you could fix is the number of overall samples you have. Say you have 10 samples, in this example 5 cats and 5 dogs, and you try to discriminate them. We can also fix, say, a certain amount of samples that might serve as a K&N decision neighborhood, or just to explore how the area, volume, however you want to call it, how the projection on the individual dimensional axis behaves the more dimensions we add, but leaving, for example, the number of samples the same. So in the following, let's assume that the number of samples stays the same. Let's say the number of samples of all of these equals 10. Okay, and I'm interested now in, well, the ratios, the properties of certain subspaces here. Okay, so just to draw this again, let's say our feature space is one-dimensional at first. Feature space over a dimension, say we have normalized it so that all of our 10 cats and dogs samples are somehow uniformly distributed along this line. It's a one-dimensional space. Now what I would like to know now is how much of that space will be occupied by a certain subset of the space, say 20%. So I'm interested in a k of 2. So 20% of that, 2 of these 10 is approximately here. This is 20% of my 10 samples. I can also view this as, say, if this is 0 to 1, so 0 to 100%, then 20% could probably also be something like 5 unit intervals. Right, so there are 5 unit intervals. This area here is covering 5 unit intervals. And the entire thing, so my entire world here, so this is absolutely not realistic for real training scenario, but my entire training set here is just 10. Okay, just let's explore what happens to our space in 2D, or if I say in 1D and in 2D and in 3D and in 100D. If I have my, say, 10 samples in 2D, then probably you can already see what's happening here. 10 samples. Somehow, well, of course, it has more space, the more dimensions there are, if I keep my samples constant. So it behaves a little bit like a gas, like particles spreading out. The more space there are, the more uniformly it will spread out. So we're always talking about uniform distributions and a constant number of training samples. Now, 20% of that space would already look something like this. Right, the 5 unit intervals would be in both dimensions. Also, each dimension is covered by 5 unit intervals, and that whole thing is 20% of my entire space here, of this area. Call it whatever you like, area, volume. We can probably characterize this by say the space that covers, and in the simplest case in the 1D, this is just a length here. I can also define a length in 2D. A length in 2D is actually an area, a sub-area, but well, we can define it like that and say this length is here. In 3D, that would be a sub-volume. But in general D, we can define that our length, so the area or the volume of whatever, equals a length at a certain dimensionality, right? A length to the power of D. So that is L, that is L square, and the cube is L cubic, and so on. Now, since I have a uniform distribution, and I know the number of overall samples I have, and in this case I'm interested in a subspace, so I know also a certain K. I can say, well, that length, that volume, that area can be approximated by the number of samples I have chosen over n, right? It's just the ratio between the small area here and the large area. Okay, so K over n is approximately what that smaller area will define. So say in our example, this is 10 and this is 2. So let's just fix this. In the original video I didn't fix this and had 2-3 different examples. So let's just make this constant and say n is 10, k is 2. Now what I can do is, if I just want to know the length, I can of course solve for this and can say, well, the length is, let's also do approximately, it's approximately k over n to the power of 1 over d. Okay, so this is what just the length, just this one side on the area, the length covered on one dimensional axis will be. Now I can explore this a bit with this knowledge. Is left over if you try to inscribe a sphere in a cube. So let's say a hypersphere into a hypercube. And if you try to do this, so here in 2D, of course, there is some area left which can't be filled by the maximum circle you can inscribe into this quad. Then you can also say, well, there is more and more space left the higher you go with the dimensionality. Now in the cube, if you inscribe, you have now suddenly 4 corners and kind of all that volume that's left over, and the more and more dimensions you include, the worse this problem will become. So the more of your samples will likely live in this area. So that spiky hairy ball is probably also a kind of illustration of how this is meant to be interpreted. It's really that in very high dimensional spaces you can imagine that each sample kind of gets its own corner. So if I would do a d-dimensional space that would characterize any cat and any dog in the world uniquely, say by an ID number, then each of these ID number is an individual corner. There is no direct connection between these corners, right? So you can probably walk all the way to the center and then back, but that is almost the same for all of these samples if you use an approach like this, so if this is 1,000 dimensions, you always need to go from the cat to the center and then back to the dog, because they are all kind of unique. There is nothing in between. It's not a three-dimensional space. It's a number of ID numbers degree of space. Okay, so I go back to my former self, and hope you enjoy the rest of the lecture.
In a general level, we would actually define a k-nearest neighbor classifier with a hypersphere. I mean, it makes more sense to build a hypersphere, but I'm not so good drawing spheres. That's why I used a cube. But what we can do, if we consider this as a hypersphere, we can look at the ratio of our entire parameter space. So like in this case, 2 dimensions, and then the hypersphere, the decision sphere here for the k-nearest neighbor classifier would be this circle here. So what we can do, we can look at the ratio between our entire parameter space and that sphere. So, and we can build that sphere a way that it will maximally fill that that parameter space. And if we look at the area of that sphere here versus the area of the green area here, so the entire parameter space, well, in 2 dimensions, it's relatively straightforward. It's pi times 0.5 squared, so it's the ratio is about 78%, so 0.785. Okay. In 3 dimensions, it's getting rapidly less. So in 3 dimensions, we have only 50% of the volume of that cube covered by an fitting sphere. And well, if we go to 10 dimensions, it's only 1%, 1.5%, so 0.0159 on 10 dimensions. So the higher dimensional the feature space, the more training samples will be in the corners of that hypercube, not only on the edges, but really they will be all assembled on the corners. And it's really hard to visualize that because our brains are so used to live in a 3-dimensional space where Euclidean distances work. But that really breaks down if we go to a really high dimensional space where we probably only compare L1 norms between vector sizes, between the representations. Now, there's a closed form solution to calculate the volume of a hypersphere in n dimensions, and what we can see is probably basically what it comes back to is that the number of features to approximate a Lipschitz continuous function is in the order of epsilon to minus d. So the higher dimension of the feature space, the more training samples you will really need in the corner to mitigate this problem, to make your decision spheres so small that they really encapsulate the nature of your embedding space here. So generalization suffers for naive classifiers here. An interesting example here is if you take your random mobile phone, smartphone, or even this video feed here, if you would like to classify how the quality of the lecture is, for example, but if you use that input space here and say your image, my SLR here has 12 megapixels on its sensor and 3 channels, then we have 36 million elements. So if we would like to build discriminate predictor with 10% error rate, so an epsilon of 0.1, then to fulfill this here, we need 10 to the power of 3.6 million, no, 10 to the power of 36 million training samples. I don't hope that I will produce that many frames in this lecture. And, you know, if you compare this, I don't know, the number of atoms in the universe is somewhere in the range 10 to the power of 100. So this is an enormous number. So we can't deal with that. And really, we need something to map down and to generate a representation that that's low dimensionally enough so that we can handle it with a relatively naive classifier. So what do we learn from all of this now? Well, first of all, a feature selection is important to build good classifiers. As we will see in this course, the key of deep learning is to learn this feature selection rather than to do this selection manually as we did it in the cats and dogs example. B, finding the right amount of features is key. Too few is very intuitive to understand, right? Just taking one might not be enough to discriminate well between cats and dogs. The other way around, selecting too many features can be quite unintuitive and requires to understand the sparsity of training samples in high dimensional spaces, right? So C, the more features we select, the sparser our training samples will be distributed in our high dimensional representation space. And they will mainly live at the boundaries there. But what this means is that the decision boundaries we might find in this space are very tight around our training examples. So that problem is known in machine learning as overfitting. Basically means your model performs well on training data, but fails completely on unseen test data. So we need to find representation spaces where this doesn't occur and where this generalization property is held up, even though the input data might be really, really high dimensional.